Let's solve together this typical related rates problem about a snowball. A snowball melts symmetrically such that it is always a sphere. Its surface area decreases at the rate of pi inches squared per minute. How fast is its radius changing at the instant when r equals 2 inches? To solve this problem, we're going to use our standard related rates problem solving strategy. We'll go through each step clearly now, and then at the end of this video, we'll include a clear summary that you can screen grab if you'd like. Now, the first step in solving any word problem is, of course, to draw a picture of the physical situation. So let's quickly sketch a sphere. And anytime we have a sphere, we automatically add a radius r, since that value will undoubtedly enter into our analysis. Now, the problem states that as the snowball melts, it always remains a sphere, and that fact is going to be crucial to our solution. The problem also tells us something about the sphere's surface area that we're going to call A. Specifically, we're told something about the rate at which the surface area decreases. That rate is dA dt, the rate at which the area A changes with respect to time t. The problem states that that rate equals negative pi inches squared per minute. You may wonder why that is a negative value. The answer is that the problem tells us the rate at which the area decreases, meaning the area becomes smaller as time progresses. And so we have to put that negative sign in by hand, translating the word decreases into a negative value for dA dt. By contrast, if we wrote dA dt as a positive value, that would mean that the area increases as time passes, which is wrong and could cost you points on an exam. Let's also note that the question is asking us, how fast is the radius changing? That is, we need to find the value of dr dt at a particular instant when r equals 2 inches. We won't actually make use of that value until the end of our solution. We notice that the problem is telling us something about dA dt and is asking us something about dr dt, and so we need a relation between those two quantities. Let's think about what that relationship means physically for a moment and focus on the area A and the radius r. Now clearly, if the snowball melts quickly, then its radius changes quickly too. By contrast, if the snowball melts more slowly, then its radius also changes more slowly. So intuitively, we expect that the rate at which r changes, dr dt, somehow scales with the rate at which the area A changes, dA dt. Our job is to find the exact relationship between those two quantities. In order to find that relation, we back up a step, and we need to develop a relation between A and r. And that takes us to the second step of our problem-solving strategy, to write an equation that relates the quantities of interest, in this case between A and r. And this is the part of the solution that for most students is most challenging when you first do related rates problems. But don't worry, with practice you'll get this down. Now for some related rates problems, to develop the relation we're after, you will use a simple geometric fact. And in this case, because the snowball always remains a sphere, that's a big clue. We know how its surface area depends on its radius. At every moment, its area is A equals 4 pi r squared. And that's either something you remember, or, if you have to, go ahead and look it up. Now, a very important point in our strategy is not to substitute r equals 2 inches yet. Anytime you have a quantity that changes as the situation in the problem progresses, don't substitute a value for it yet. Here, remember, the snowball melts as time passes, which means the radius changes. It isn't 2 inches at all times. And so we leave the radius as the variable r for now. We'll substitute r equals 2 inches at the end of our solution. Now our equation a equals 4 pi r squared completes the second step of our problem-solving strategy, since we have the relation between a and r that we need. And we can now move on to the third step and take the derivative with respect to time of both sides of our equation, remembering the chain rule when we do so. The derivative of the left-hand side of the equation gives us d dt of the sphere's area is A. And that equals the derivative of the right side of the equation, d dt of 4 pi r squared. Now the left-hand side, the derivative with respect to time t of the surface area A, is the rate dA dt. And we know its value, negative pi inches squared per minute, and we'll make that substitution very soon. On the right side of the equation, we can pull 4 pi out since that's a constant. And we're left with the derivative d dt of r squared. And that derivative is 2r dr dt. The 2r part is probably clear to you. If the dr dt part is also clear to you, you can use the link you should now see to skip over the next part of our discussion, which is a detour for a bit, to discuss specifically why that dr dt term is there. The key thing to realize is that we're taking the derivative here with respect to time t. Specifically, while the derivative with respect to r of r squared is 2r, the derivative with respect to time t of r squared is 2r times dr dt. Why is that dr dt there? To answer that question, let's go back to our expression for the sphere's area, A equals 4 pi r squared. But now let's explicitly show the time dependence of both A and r, which are both functions of time t. So we'll show them as such just to emphasize the point. Let's again take the derivative with respect to time of both sides of the equation. So we have d dt of area as a function of time t equals d dt of 4 pi, radius as a function of time, squared. Now the left-hand side, the derivative with respect to time t of the surface area A, is the rate dA dt. On the right-hand side of the equation, we can pull 4 pi out since that's a constant, and we're left with the derivative d dt of something in brackets that's squared. As usual, when we take the derivative, the 2 comes down in front, and we have 4 pi times 2 times that thing in brackets, which is r of t. But we also have to remember the chain rule and apply d dt to what's inside the brackets, which gives us the chain rule term d dt of r of t. Let's be clear, r is a function of time t, even though we don't know exactly what that function is. It doesn't matter. Whatever the function is, it has a derivative with respect to time t, and that is this term d dt of r of t. This dr dt term, due to the chain rule, is very important when you're solving related rates problems, and it's easy to forget. Though if you do forget it, you'll probably realize something is wrong when you don't have any rate dr dt on the right-hand side of your equation, and so you haven't successfully related the two rates you need to relate. Many beginning students do initially forget that term, and then remember to go back and put it in later. That's fine, as long as you do remember to correct the omission at some point. Now this last term, d dt of r of t, is the rate dr dt. And so we now see how the rates dA dt and dr dt are related. Remember that we explicitly wrote the area A and the radius r here as functions of time in order to emphasize why the chain rule term dr dt is there. Typically you would never write all that out, instead just writing A equals 4 pi r squared as we did earlier, and then taking your derivatives and working your way to the result 4 pi times 2r times dr dt, of course remembering the chain rule term there. The math is all the same. We're now just not writing out all the explicit time dependencies. So with that, let's return to where we were in our solution. Simple multiplication of 4 times 2 gives us 8, and so we have 8 pi r dr dt. And that completes the third step of our problem-solving strategy, since we now have the relation between dA dt and dr dt that we need. The last step of our strategy is simply to solve for the quantity we're after. Remember, the problem has asked for dr dt at a particular moment. So let's first swap the two sides of that last equation. to put dr dt on the left-hand side and dA dt on the right. And then let's divide both sides by 8 pi r, so we get rid of that from the left, leaving dr dt equals 1 over 8 pi r times dA dt. And with that, we're ready to substitute values. Starting first with r, remember that the problem told us that we want to know dr dt at the moment when r equals 2 inches, so this is the time to make that substitution. And we need dA dt, which the problem told us equals negative pi inches squared per minute. And so now we're just left with some simple math. The pi's cancel, and so numerically we have negative 1 over 8 times 2, or negative 1/16. Units-wise, the inches in the denominator cancels one of the inches in the numerator, and so we have inches per minute. And that is our final answer. dr dt equals negative 1/16 inches per minute. We can ask, do the units make sense? The answer is yes. We expect the radius to be changing at a rate that has units of inches per minute, as opposed to, say, inches squared per minute, or minute per inch, or anything else. We can also ask, does it make sense that dr dt has a negative value? And again, the answer is yes, for the same reason that dA dt has a negative value. Both the area and the radius decrease as time progresses, and so those negative signs must be there. That brings us to one important warning. If you are using a web-based homework system, and the problem asks, at what rate is the radius decreasing? Note that that's a slightly different question than the one at the top of the screen, which asks, how fast is the radius changing? The answer to how fast the radius is changing is negative 1/16 inches per minute, because r is decreasing. On the other hand, when the web-based question asks, at what rate is the radius decreasing, they've already taken that negative sign into account, and so you must enter a positive value, positive 1/16, to be marked correct by the system. By contrast, if you enter a negative value, it will be marked incorrect, leaving many students frustrated since the system doesn't give any useful feedback about what you're doing wrong. Now, we promised earlier we'd present a summary screen of the steps we use to solve this problem so that you can screen grab it if you'd like, and here that is. We use these same 4 steps to solve every related rates problem we encounter. In a minute, you'll see a list of some of our other videos that illustrate the approach to solve other problems. Please note that in step 2, not every problem will use a simple geometric fact to develop the equation you need. Instead, you need to know 4 different approaches that cover essentially all related rates problems. We've listed each of those in our general problem-solving strategy for related rates problems. You can find that list, along with this entire problem-solving strategy, at our website, mathino.com. You'll also find there an example of each of the 4 types of related rates problems, every one of them with a full solution that uses this exact same strategy. For now, we suggest, as always, that you immediately, right now, try to solve this problem for yourself to make the solution your own. After all, the goal is for you to be able to do it rather than just watching us solve the problem. You need to be able to do it routinely. So give it a go. If you'd like, you can use our problem-solving strategy as a guide. And as a reminder, the answer is negative 1/16 inches per minute. And of course, if you have a question about anything we've done, or any suggestions for us, please let us know, and we'll do our best to answer.